Hello, this is video number 8 in the PETTaLS version 1.7 video tutorial series. This video is going to be about the impulse response window. So PETTaLS is an application I wrote, the pretty good exciter and tactile transducer loudspeaker simulator that can be used for designing and simulating loudspeakers made from exciters attached to surfaces like windows or pieces of cardboard or aluminum or anything else you can think of, really, as long as it's simulatable, let's say. So I have a set of results here for an impulse response that correspond to the frequency response shown here, and this is the simulation that you can run with the default sets of parameters that come up when you start the program, which are acrylic or plexiglass panel, 3 millimeters thick, clamped at all 4 edges, 23 centimeters wide by 35 centimeters tall, with a DAEX19CT4 small exciter smack dab in the middle of the panel, which setup looks like this. Here's the size and dimensions of the panel. Here's the exciter right in the middle. And if I want to see what this is doing at any frequency, I can type in a frequency here and see the vibrational pattern. So that's 250 hertz. Let's do 750 hertz for the fun of it. Let's do 2000 hertz. Let's do 15,000 hertz. Wow, look at that. The vibrations are coming from the center of the ring where it attaches to the panel at that frequency. So there are a number of ways that I could have plotted the impulse response, and in previous versions of the program, which I think you can still go download on GitHub, they might have other ways of looking at the impulse response. This is a spectrogram of the impulse response, which is a time frequency display. So time versus amplitude display would be like a ringing response. This is the time frequency display of that same information. So frequency is on the x-axis, which matches the frequency bar down here, and time is on the y-axis, which goes from 0 to 100 milliseconds to 200 milliseconds. So you can see ringing, which are vertical columns of brighter and brighter information. Red is the loudest. That decay over time. And these are going to correspond to the peaks in the impulse response, so the vertical bars of ringing. So peaks in the frequency response create ringing in the impulse response. That might be something that you want to avoid depending on what your design is. There's all sorts of different designs, so I don't know. It depends what you're going for. This will also change with what location you're choosing to plot. So, for example, I'm looking at the on-axis frequency response, which would be anechoic. I like personally looking at the average horizon level because this is probably what you're more likely to see with room reflections, is something like this. And so you can see that the impulse response changed 2 to match the new frequency response. If I go to the off-axis views, the impulse response will change to match those as well. So let's just take a look at all of them. Yeah, so minus 90 and 90 match because the exciter is right in the middle of the panel. Cool. Let's just go back to average horizon level for the fun of it. Okay, I'm going to do a different simulation that can be used to illustrate what happens with these more concretely. So let me go to an aluminum panel, still 3 millimeters thick, which is pretty thick aluminum. And I'm going to do free on the top and the bottom. Or no, sorry, free on the left and the right, and simply supported on the top and the bottom. And I'll do 5 millimeters thick or 5 centimeters thick by 50 centimeters tall. And center exciter still in the center. So let's see. Let me just make sure that this looks like what I want it to look like. Yep. Okay, so the ringing time of the modes in the loudspeaker and the sharpness of the modes in the frequency response is proportional to this quality factor for the material. This is something that's really hard to define. Like, you can't just look up aluminum quality factor because it depends on all sorts of things, like the boundary conditions and whatnot. And quality factor is not a property of a material. It's a property of a mode or of a peak in a frequency response. So I can be extremely reductive and say all of the modes in a structure are going to have the same quality factor, and it's based solely on the material, which sometimes is kind of true and is a better estimate than anything else I have available to me right now. So you can sort of think of it as the quality factor gets higher as the ringing time of that material gets longer. So if you were to make a wine glass out of this material and hold and tap the wine glass, would it ring for a long time or would it not ring? So aluminum, yes. Maybe I don't want to change this in the middle of a simulation. Actually, it's not going to do anything. Glass, I put 50 because glass rings for a long time. Acrylic, I made 10 because in a plastic wine glass, it just goes thud, doesn't ring. Steel, I made 40. So these are all estimates, but they're good enough. So the higher the quality factor, the longer the material rings for. Okay, this is still going. I'll be back when this is done so that we can look at the results. Okay, look at that. We've got some results. And the reason why I did that simulation is because we've got really discrete, clear peaks in the frequency response that lead to really clear columns in ringing in the impulse response. So you can kind of match up, you know, this peak goes with this column, this peak goes with this one, doop, doop, doop. I think this is where the horizontal modes start kicking in, so we get suddenly a big increase in volume, because all of a sudden there's a lot more modes here. Until that point, it's all vertical modes. If I made the panel skinnier, that would probably go away. This peak doesn't get a higher Q because it's sort of damped by the exciter. Or actually, no, this is the exciter. This is the lowest mode of the panel. So, yeah, that one, this is all damped essentially by the exciter. So this one dies out pretty quickly, but then these sharper peaks that aren't damped by the exciter continue on for longer. So let's compare that to, let's just say that we can magically increase the Q of our material or our panel setup somehow to 200. So sharper peaks. Let's see what happens now when I run the simulation. Okay, so with the higher Q, a Q of 200, we do see sharper peaks in the frequency response, although not that much sharper, and that could be because of the frequency resolution, or it could just be because, you know, there's a limit to how sharp, like, you aren't going to get infinite dB if you keep just setting the Q higher and higher. There's a limit to that. So these vertical stripes in the impulse response are going to ring for longer because these peaks are sharper. So if you rewind the video a little bit and look at the old ones, they probably aren't quite as bright for quite as long. So higher Q leads to sharper peaks and longer ringing in the impulse response. Let's compare that now to a really low Q. I'm going to set this to a Q of 2, and it's interesting to compare the vibrational shapes that appear with a Q of 2 to the higher Q. The waves don't really spread on the panel with a low Q. All of that energy gets absorbed. And so you don't really see these checkerboard patterns very often, except maybe at lower frequencies where the wavelengths are longer. And because of that, we're not really going to see a whole lot of ringing in the impulse response. So I'll be back when this simulation is done running then. All right, so the new yellow line here is the frequency response average horizon level of the really low Q speaker. So there are still some stripes in the impulse response, but those, so let me take off compare results. You can see the peaks are like not hardly even there anymore with the low Q. Those actually correspond to little discontinuities in the frequency response. Like if I look at this stripe here and then I zoom in, there's a discontinuity in the frequency response because my frequency resolution isn't super high at that frequency. And so when I convert that to a linearly spaced frequency response and then do the inverse Fourier transform, it gives me a little blip right there. So I wouldn't take that very seriously. This is kind of more of an estimated impulse response because I have to convert the logarithmically spaced frequency response to a linearly spaced frequency response and then convert that to the impulse response. So it's kind of estimated, which leads to some artifacts like these things here. Now, it's kind of tough to do this graphics-wise, but you can spin this thing around and turn it into a waterfall plot if you want. Let's see if my computer will be nice to me and let me do that. There we go. Okay. Depending on how good your graphics card is, that might be a little faster process. So we can see that those little glitches there are kind of insignificant amplitude-wise compared to this big red peak right here. That's what's kind of dominating this frequency response. So yeah, those little glitches actually cause these funny the stripes here, which look like echoes. But I don't think those are really there. They just happen to be kind of more significant than anything else because the frequency response is so flat and smooth. Okay, cool. Hopefully that helps. That's all for this video, and I'll be making video 9 here shortly. See you there.